Yeah.
Okay, but then I point this way. Okay, good. That's okay. Hi, sorry. It's really a great pleasure to be speaking here. I have been following AI actually since I was 20 years old. AI is a field that was really started in the 50s and 60s, but of course without computer power, it was very difficult to do things. Plus we've learned so much about how to actually learn from data and not overlearn. I think, and every single year there are new improvements. Every single month there are new improvements. I just wanted to say something about multi-scale modeling because it isn't always understood what it means. And basically, for me, it means choosing a model that isn't too simple and isn't too complicated. The right level of model. And I think we do this all the time. Whenever you tell somebody a story, you don't start with all the details, you pick the right level. And this is true particularly for AI. Although AI has models that seem to be very, very complicated. Loose? Take this off. Okay. So today I'm actually going to be talking about something, I don't know. I hope it's okay for everyone else. I mean, the flashing doesn't worry me, but
It's okay.
and you have to look that way, right?
Yeah. You throw it that way.
So don't, it's very strange to talk. Maybe I should stand there. I don't know. I mean, I feel strange here talking to your backs. Anyway, so this is based on work that I've been working on since the end of January 2020. 660 days ago, I started to work on, wait, I can't do this. It doesn't make any sense to have the screen here and the screen here. It always surprises me that we talk about AI, and in every single place, the screens don't work. One advice I would give to everyone, buy Apple TV. Apple TV, anyone on the network. You don't need cable, you don't need nothing. Okay, great. Fine, sorry, okay. So, I'm going to put this back again, it should be fine. Okay, so I have been working on coronavirus and COVID-19 since the very beginning. In fact, I wrote a report on the 1st of February, which I sent to friends on WeChat, but somebody translated it into Chinese, and it was seen by many millions of people. So what did this report say? It basically, in this report, I looked at, I don't know, okay. Is it my computer?
Yeah, the connection between the system.
I mean, I'm happy to change the, but then I need a USB stick. Sorry. Hope it will be okay now. So just to start again, I'm Michael Levitt. I want to tell you about my experiences studying COVID-19 from the very beginning. I started with the outbreaks in China. My first report was actually written So I'll be telling you about my experience with COVID. It started out with a report that I wrote on the 1st of February 2020, sent it out to many, many friends in China by wishing, also by WhatsApp to friends in America. I didn't expect it to be published, but somebody had it translated into Chinese and released it. And it was an important report because it basically said that I thought that COVID in China was actually slowing down. Now, this is at the end of January, when everyone was sure that COVID was speeding up. And why I reached that conclusion, there are many different ways to analyze an epidemic. New cases, daily cases, total cases. And I decided to do something also very simple, to look at the ratio of cases today divided by cases yesterday. And the reason is, if you look at your bank account and you're getting 5% interest, then each day or each month you should have 1.5. The ratio between today and yesterday should be a fixed number. So for exponential growth, you would expect this to be a line like this. But in reality, the line is coming down. The peak was, I think, something like the 24th of January, and then we see the points coming down. Now, at that time, I wrongly thought that it was a straight line. But when this comes down to 1, if today is the same as yesterday, the pandemic is over. So basically, these things gave me hope that things were decreasing. And in fact, by the 28th of February, it was basically essentially over. Now, this really got me very involved because I had been made public on the 2nd of February. I wrote a report every single day. In February, I wrote 24 reports. And then at the same time, other pandemics started. We had the pandemic or the epidemic on the Diamond Princess cruise ship. That gave us a good idea of how many people would die if the infection was very high. The infection on the Diamond Princess cruise ship was 20%. 80% of the people were over 70 years old because the old people go on cruises, but only 7 died. So the death rate was about 1 in 200 for the old people. And there's high infection. So that gave us another idea. Anyway, we continued, backwards, to look at this. So what we found very important, as I just said, is to look at, this is today, x of t, and this is yesterday. T is just time. And also very important is to look at this here, which is the log of this number. Unfortunately, this should be R. This is the exponential growth rate. So if you have that today is yesterday exponential of something, it's the exponential of this. It's very simple algebra to see that. That ends up being a very fundamental property. If growth is exponential, this should be fixed. And this should be just a constant times that. It's very important because people were very, very concerned about exponential growth. Okay, so now let's try to see what we would expect. A very important thing that I guess a physicist doesn't understand something. He looks at model systems. And here are 3 model systems. So this one is, if you like, every government's dream. Corona is growing exponentially along the black line, and suddenly we say, stop. Everyone is quarantined, everyone is separated, it stops. If you now look at the number of new cases, it increases exponentially and then stops. If you do the same thing on a log scale, which is the log scale here, then the number of cases is increasing linearly on a log scale, and it stops. Pure exponential growth. Cases also increase exponentially, because the derivative of an exponential is an exponential. So then also here you see the slope of this, which is fixed. And here you see an approximation to the epidemiological reproduction number. This is something that newspapers have been using everywhere in the world, the famous R number. And for this kind of growth, R is about 2, and then it stops when you stop it. R is constant 2, and then stops. Here is the logistics function, which occurs all the time in AI. Just a saturation function where it starts here and stops. But this actually looks very much like this ideal case. So here, on an exponential scale, things are growing on a straight line, and then they stop. They stop more slowly. It isn't a sudden stop. It's basically a saturation stop. And the number of new cases is symmetrical in a log scale as well. And again here, this, instead of being flat and sharp, it's flat and smooth. And the R number is again doing exactly the same thing, but smoothly. Now, it turns out Now, I'll show this to you, that neither of these are how COVID grows anywhere in the world. And now we have hundreds of places in the world, many, many millions of individual cases. What you find is that COVID doesn't grow according to capped exponential or logistics, it grows according to Gompertz. So I didn't give equations here, but essentially this is the logistics function. The Gompertz function is exponential growth, where the exponential growth factor is decreasing exponentially. That growth is very, very different from logistics growth. So firstly, the peak is asymmetrical. The black line looks very similar. This black line and this black line look very similar. But on a log scale, they look very different. Here, this is increasing exponentially. And here, this is just shooting up, but curving all the time. So the Gompertz growth is much faster than exponential, but it's slowing down all the time. So if you like, exponential is like a car going at constant rate on a log scale. Exponential growth is going incredibly quickly at the beginning, but the brakes are on all the time. If we look at the acceleration is high at the beginning, but going down. And this is what the reproduction number looks like. Here the reproduction number is constant. It makes sense to say it's 2, it's 2.1, it's 1.9. If the reproduction number is dropping exponentially by itself, it makes no sense to say that. So let's just say a few more things about that. So basically what you find is that this is just the logistics, the Gompertz. Logistics takes 100 days to get to the same level as Gompertz gets in 1 week. This explains why it was such a big surprise in Wuhan, why it was such a big surprise in Lombardy and in New York City. Each one, you have one case, and 1 week later, you have 1,000 cases. And I'm not going to explain to you why, but the talk in a little while of my collaborator, Francesco Zonta, will explain to you why this is. And it's a consequence of the social network. Okay, this is just showing that the effective reproduction number in the Gompertz starts out at 100. That means the average person is infecting 100 people. How can that be? Epidemiologists just said, this is artifact. We forget about this. But it's not artifact. Okay, now what do real cases look like? So this is China outside Hubei. And you see that this blue line, which is the exponential growth rate on a log scale, is a straight line. For logistics, it should be a level line, it's decreasing. Exactly the same thing in South Korea. Exactly the same thing in New Zealand. Very early on, people said, we don't believe the Chinese data. And I said, well, this is Chinese data. This is New Zealand data 2 months later. If this data is not accurate, then China must have a time machine. So we can see what New Zealand will do and copy it, because these are so similar. And then we have other places. This is cases with lots of cases. Lombardy, Northern Italy was very bad. Again, going down. And you can see this curve is coming very quickly. New York City. New York City had the worst, New York State had the worst corona of any place in the world by a factor of 3. There were more deaths compared to normal death there than anywhere else. And again, and finally, Austria was a case where this seems to be flat, but it goes down. It also ends up being more Gompertz than logistics. Okay. This just shows many places, and wherever you look, the blue line is going down. Over here, but everywhere, it's going down. This is US Massachusetts, that's Italy, Tuscany, New York City, US Connecticut, China, going down very quickly. Everywhere it's going down, which means everywhere is growing by Gompertz. There's no place we found where there's an early outbreak. One problem is that you can have 2 outbreaks in the same country. You can have 10 outbreaks in different places, and they add them together when they release the numbers. And if you can't distinguish between that, then if you have 1 outbreak and then a new outbreak starts, you think it's accelerated, but it's just adding more counts from somewhere else. This just shows those cases I showed you before of Lombardy, New York State, and Austria, fitted by Gompertz and fitted by logistics. And the residual is more than 3 times lower for the Gompertz fit than for the logistics fit. So it seems very, very convincing. Okay. Now this just shows the reproduction number is actually calculated by epidemiologists using Bayesian likelihood and things like that. So I actually took their program and I applied their program to my 2 test cases, logistics function and Gompertz function, and then to 2 real cases, Lombardy and New York State. And here you can see that the logistics function is around 2 and goes down. These are all pure logistics growth without any intervention. You're not changing anything. It's just pure logistics growth. Gompertz starts at around 100 and drops all the time. And what we see very, very clearly is that these real examples look much more like this than like this. This is using their program on public data. So every epidemiologist should have seen that, and this is a log scale. So for example, for the first 2 weeks, Lombardy had an R value of over 4 and started out at 100. I never heard this from anybody. They're all talking about the R going up and down as we imply intervention. You wear masks, the R goes down. Well, if the R looks like this naturally, it may be going up and down, but it's very hard to see. When something is decreasing exponentially, if the exponential decrease rate changes slightly, not easy to see. This just compares the exponential and logistics. So firstly, you see here that basically this is the slow growth. Exponential is actually slow. Because if you think about it, if you're doubling every 3 days, that's quick doubling. 1 to 2 to 4 to 8. To get to 1,000 is 10 doublings. That's already 30 days. The Gompertz just start quickly and get to this point very, very quickly. So there's a much faster rise of the Gompertz than the logistics. But here shows very much that the reproductive value for the logistics is flat. Sorry. Whereas the reproductive value for the Gompertz starts in the hundreds, here it's starting at 45 and dropping down. Okay. This just shows something at the very end, something I just did yesterday. Can we predict what a pandemic is doing? Now, it turns out this is New Zealand, actually today. And I was reading a newspaper report saying how New Zealand is now going crazy. The hospitals will be flooded, and if you look at it, it looks pretty scary. This is the number of new cases just increasing on a scale. Okay. So it turns out that what you can do, there are multiple outbreaks. There was an outbreak here that went away, a little outbreak, another outbreak, and then an outbreak here. But this outbreak starts before this outbreak is finished. So what you can do is you can find the minimum here, like this point here, and subtract that from all of these. And when you do that, you find, much to my surprise, that this log scale R, reproductive, the log of the exponential growth rate is decreasing linearly. And you predict that when it hits a certain value, it's the maximum. But it's been decreasing linearly for 25 days. There are ups and downs. So this gives us very good confidence that New Zealand will reach a peak in about, I don't know, maybe even by now. Some of the data is delayed. No, this is maybe in 2 weeks' time. Gives you very clear, and this can work anywhere because you could always subtract the baseline. And the real reason is that the logistics function doesn't tell you where it's going. Because initially, if you look over here, this is the acceleration, and the acceleration is flat until it goes down. Gompertz, if you have a function decreasing like this and you're over here, it's very easy to extrapolate a straight line. More easy than anything. There's uncertainty, But because the Gompertz function is driven by a straight line, and the straight line drives it, the straight line drives it from the very beginning. This starts out flat and is then driven by a straight line decreasing. This, for case number 1, is already a straight line going down. That's just the nature, because it's an exponential growing exponentially, and the rate constant of the second exponential is a fixed number. So this basically changes the whole view. Any single outbreak is fairly easy just to wait. The big thing is going from an infected area to an uninfected area. You may want to do that intentionally. Sweden decided to rely on herd immunity and let the infection spread easily. And when you actually look at the data for Sweden, which I actually have here, sorry, I'm used to my own and not this one. Sweden, oh, I don't see it, but Sweden has a very wide peak. Sweden did not try to control. Sweden just kept it going as much as possible, got everyone herd immunity, and there's been no Delta wave in Sweden. Sweden has less excess death than almost any country that releases excess death, except, say, the province of Taiwan, where everything was closed down. Now, other places didn't do so well. In the United States, we have family living in the United States, and while the United States, I'm just looking for Sweden, but I'm not going to find it. In the United States, while New York had terrible, terrible COVID, planes were flying from New York City to Europe and to all of the United States every single day. So that's not a good thing. Maybe it is a good thing. It depends what you want to do. New York had really, really bad COVID, but then it saturated. New York in 7 weeks burnt all the COVID out. Now you might ask, how many people died during that time? In New York, 99.7% survived. 0.3% died. But that was the price they paid. They could have opened up. There was no second wave, no third wave in New York City. In other places, there were really, really quite bad additional waves. So I think the policy is unclear. What you can do is you can stop spread. If you simply close down all transportation, then there's no way it will get from Shanghai to any other city. And in Shanghai itself, the key thing is to stop people going a long way away. Inside a given area, because of the because the Gompertz function is so strong at the beginning, by the time you notice the first case, you probably have 1,000 cases. And these cases are everywhere. So it's very, very hard to control at the beginning. The only way you can control at the beginning is not letting it get there. And this was the mistake that happened in Lombardy and the mistake that happened in New York City. Anyway, I think I'm done. Just to say that there's a lot of controversy about this. My hero in science actually is Max Perutz. He's the person who invented protein crystallography. And he said that in science, truth always wins. We can do whatever we like now. People will look back 10 years' time and say, how bad was COVID? What was the right thing to do? And unfortunately, it's very political everywhere. Terribly political. But it is also a very important, it's a scientific problem. How do you control a pandemic? It seems to me you have to have good data, and this time we actually I haven't seen any data, even from Iran, even from Iraq, even from India, that looked like bad data. One good thing is that we use the ratio of today to tomorrow. So if all the data is wrong by a factor of 10, it doesn't matter because the ratio is unchanged. So you can count the data any way you like. You can count deaths, you can count cases. But I think we are going to see truth being winning. Anyway, thank you all for your attention. Sorry.
I do have some questions.
Sure.
So, Michael, with the past few weeks in Japan and Florida, it seems like over how many 2 weeks or about 2 months, then suddenly
I think the thing is, I've got something I can show you. Just a second, if I. Okay. So what we're seeing here is this is the excess death. This is not the reported death. This is actually the real death found by just reporting deaths and estimating how much death you would expect based on previous years. So, the pink is for people over 65, and the green is for people under 65. This is the baseline. So what you see in New York is that in the spring, week 13 of 2020, there was a lot of young people there, and a huge amount of old people there. That peak is 7 times higher than this baseline. So in the worst week in New York, 7 times more people died than in a normal week. That's New York. But basically, after that, there was a small wave here. Remember, people die.
Right.
If I just came and walked along the street, putting a blue mark on random people's hands, I would find that some people with blue marks die. Especially if I look at old people. If I just walked around in the street, and whenever I saw an old person put a blue mark on their hands, and then said, I'm killing people with blue marks, I would definitely find, because in a natural society, almost 1% die every year. We live about 100, so it makes sense. Okay, this is New York. Let's see what happens for somewhere else. You asked about Florida. So what happened in Florida is,
for the Delta case.
this is Delta here.
The Delta, yeah.
But
Suddenly disappeared.
a Delta is bad. It actually kills a lot of young people, but only in America. I'll show you something else. This is all very, very new data. So this is all of the United States added together. First wave, second wave, third wave, Delta. And there are Delta deaths. We now go to do exactly the same thing. The worst Delta was in the United Kingdom. There were almost 4 million cases of Delta. So what do we see? This is where Delta is. This is July this year. So in the United Kingdom, there has been no excess death since March 2021. No sign of Delta, not for old people and not for young people. Nothing. If you do the same thing for the United States, you see a lot of Delta. And what's scary here is that in this first wave, young people were much less than old people. I call over 65 old and under 65 young. You could choose another number. In this wave, this is the same as this. Now we do one other thing. We go to all of Europe. Europe, just adding up all the countries in Europe, it's 430 million people, bigger than the United States. So we see big wave for old people, almost nothing for young people. Big wave, really nothing. And now, this is where Delta is in, and Europe includes Britain. Euromoma is a database that collects excess death for many places in the world. And I just added up all the ones in Europe. And you can see, so the Delta wave in Europe, so there's something else going on. Something in the United States and in Britain not in Britain, in the United States, is killing young people. I don't know what it is, but if you look at that curve compared to this curve, remember here also, this is the expected death for young people. This is the real death. And you can see this one, for the old people, it goes up and down, but this is basically high all the time. It's as if from the 13th week, I think, is probably the 21st of March, or 3 weeks, January, February, March. End of March would be 13 weeks. After week 13, suddenly young people have a death rate that is increased by 20%. And it stays there. That is, for me, really scary. And it's true everywhere. I mean, this is Florida, goes up, stays there. New York's an exception, but there's Texas, goes up, stays there. So something is wrong. The Delta wave in healthy countries is doing nothing. I mean, Britain is such a clear case because we've all heard so much about Delta in Britain, and these numbers have nothing to do with reported cases. This is just looking at how many people die, very simple number, and how old they are. And these numbers are used by epidemiologists to detect flu. Another thing that happened during COVID, flu. From this 13th week of 2020, flu disappeared from the whole world. No one knows why. But this has an interesting effect because, and I didn't put this into my talk, I didn't just speak so long. If you look at excess death, there are 4 countries that have negative excess death, which means less people died than you would expect. Now, one trouble is that excess death is only reported by about 40 countries in the whole world. All the United States states and another 37 countries. Not China. But the 4 countries, or the 4 locations that have negative excess death and report the data are South Korea, Australia, New Zealand, and the province of Taiwan. And they all have about 6% less death than you expect. Or, what is going on? Turns out what is going on, there's no COVID in those places, and also no flu. This means that we're saving 6% of the lives. But this is not necessarily a good thing, because these are people, the people who die of flu are always the people who are least healthy, old and least healthy. They're not dying anymore because there's no flu. So this means that there's an accumulation of older people. In China, almost 1 million. So the next flu attack in China is going to be really, really bad. We have no earlier flu on which to base the vaccine. Normally vaccines for the Northern Hemisphere are based in flu in the Southern Hemisphere 6 months before. We have nothing. It's kind of scary. Plus we have an accumulation. So actually for flu, the safest place to be is the United States, because the corona has been so thoroughly there that they don't have any old people to push the flu. Anyway, sorry, I've been talking too much. I can talk for 3 hours on this.